Hello everyone. Welcome to my YouTube channel on engineering mathematics. In this video, I'm going to discuss a technique or rule from integral calculus called as differentiation under integral sign. So let us first see some of the key features of differentiation under integral sign. Differentiation under integral sign is an operation in integral calculus which is used to evaluate certain integrals. Under fairly loose conditions on the function being integrated, differentiation under integral sign allows one to interchange the order of integration and differentiation. Many integrals that would have otherwise be impossible to evaluate or require significantly more complex methods to evaluate can be solved by using this technique or approach. So let us see what is this rule of differentiation under integral sign. Let us consider an integral of f of x comma alpha dx over the limit a to b as I of alpha. Note that here x is the variable and alpha is parameter. If f of x comma alpha and partial derivative of f with respect to alpha, that is dabba f by dabba alpha, are continuous functions of x and alpha, then by differentiating both sides with respect to alpha, we get di by d alpha is equal to d by d alpha of this integral. Then according to this rule of DUIS, we can interchange the order of integration and derivative. So we get integration of partial derivative of f with respect to alpha. Since this function f is a function of two variables x and alpha, derivative of f with respect to alpha will be partial. So by rule of DUIS, we can say di by d alpha is integral of partial derivative of f with respect to alpha dx over the limit a to b. Now let me show you the use of DUIS rule while evaluating certain integrals with one parameter. So I call these examples as type 1 examples. Look at this first example. Here we are asked to prove value of the integral of x raised to a minus 1 upon log x dx over the limit 0 to 1 is equal to log of 1 plus a for all a greater than or is equal to 0. Now, since this integral has a as its parameter, we call this integral as I of a. We label this statement as 1. Now we use DUIS technique and we differentiate both sides of this equation with respect to a. So on LHS, we get di by dA, and on RHS, we get integral of partial derivative of this integrand with respect to a. Since we are differentiating with respect to a, we have to keep other variable, that is x, constant. So this log x is constant. Now we differentiate x raised to a. Differentiation of x raised to a with respect to a is x raised to a into log x, and derivative of 1 is 0. Now this log x and this log x will get cancelled. Only x raised to a will be left as an integrand. Now integration of x raised to a is x raised to a plus 1 upon a plus 1 over these limits 0 to 1. Now we will substitute these limits one by one. When we substitute x is equal to 1, we get 1 raised to a plus 1, that is 1 upon a plus 1, minus, after substituting 0 in x, we get 0 raised to a plus 1, that is 0. So value of di by dA is 1 upon a plus 1. Now we integrate both the sides with respect to a to get value of I. So after integration, LHS will be I of a, and on RHS we will have integration of 1 upon a plus 1 dA. Integration of 1 upon a plus 1 is log of a plus 1 with integration constant c. Now we will evaluate value of c by substituting one of these limits into this equation. We call this equation as equation number 2. So let us substitute a is equal to 0 into this equation. So we get I of 0 is equal to log of 0 plus 1, that is log 1 plus c. Now we will try to find out value of I of 0 from equation number 1. In equation number 1, we will substitute a is equal to 0 to get value of I of 0. So we see I of 0 is integration of x raised to 0 minus 1 upon log x dx over the limit 0 to 1. But x raised to 0 or anything raised to 0 is always 1, and 1 minus 1 is 0. 0 upon log x is also 0. So integral of 0 is 0. So we see I of 0 is 0. Now we put this value of I of 0 back into this equation. We see c is equal to 0. Now we substitute value of c in equation number 2. So from equation 2, we get I of a is equal to log of a plus 1, which is the required RHS. I hope you understood steps involved in this solution. Now let us go ahead for next example. Here we are asked to prove value of the integral of log of 1 plus ax square upon x square dx over the limit 0 to infinity is equal to pi into under root of a for a greater than 0. Now since this integral has a as its parameter, we call this integral as I of a, and we label this equation as equation number 1. Now using DUIS rule, we differentiate both sides of this equation with respect to a. So on LHS we will have di by dA, and on RHS we will have integral of partial derivative of this integrand with respect to a, keeping x constant. So this 1 by x square is constant. Derivative of log of 1 plus ax square with respect to a will be 1 upon 1 plus ax square into derivative of 1 plus ax square, that is x square. Now this x square and x square will get cancelled. Only 1 upon 1 plus ax square will be left as an integrand. Now to solve this integral, we will take out this a. So we have 1 by a outside, and inside the integral we will have 1 upon 1 by a plus x square dx. Now at this point I would like to remind you the integral of 1 upon alpha square plus x square dx, which is nothing but 1 by alpha into tan inverse of x by alpha, which is this. So here if you compare this 1 by a with alpha square, we will see alpha is equal to 1 by root a. So let's apply this formula over here. We get 1 by a into 1 by root a into tan inverse of x by 1 by root a over the limit 0 to infinity. Now let's substitute these limits in x. When we put infinity in x, we get tan inverse of infinity, that is pi by 2. And when we substitute 0 in x, we get tan inverse of 0, that is 0. This a into 1 by root a will become 1 by root a, and inside the bracket we will get pi by 2 minus 0. So di by dA's value is pi by 2 root a. Let us carry forward this statement. Next, we will integrate both the sides to get value of I of a. So after integrating both sides, on LHS we will have I of a, and on RHS we will have integral of pi by 2 root a into dA. This pi by 2 is constant, we can take it out. So we will have integral of 1 by root a dA. Integral of 1 by root a dA is 2 root a. So this 2 and 2 will get cancelled. We will be left with pi root a plus c, where c is an integration constant. Now we have to find value of this constant c. To do so, we will substitute one of these limits for a. So by substituting a is equal to 0 in this equation number 2, we get I of 0 is equal to pi into root of 0 plus c. So pi into root of 0 is 0. So we get c is equal to I of 0. Now to find out value of I of 0, we will refer equation number 1 where we are given statement for I of a. In this statement, we will put a is equal to 0 to get I of 0. So we see I of 0 is integral of log of 1 plus 0 upon x square dx. But log of 1 is 0 and 0 upon x square is 0. So integral of 0 is 0. Therefore, I of 0 is 0. Finally, we substitute value of I of 0 in this equation. So we see value of c is also 0. Now we substitute value of c in equation number 2 to get value of I of a. So I of a is pi root a as required. Hence proved. Now let us go ahead for next example. Here I have extended previous example and asked to deduce value of the integral log of 1 plus x square upon x square dx over the limit 0 to infinity. Note that we just proved value of this integral of log of 1 plus ax square upon x square dx over the limit 0 to infinity as pi root a. And to find the value of this integral, we just have to put a is equal to 1 into this statement. So after substituting a is equal to 1 into this statement, we see value of this integral is pi into root 1, that is just pi. Hence, this integral is deduced as pi. Let us see next example. Here we are asked to prove value of the integral e raised to minus ax into sin x upon x dx over the limit 0 to infinity as cot inverse of a. Let us consider this integral as I of a and label this statement as 1. Now we apply DUIS rule and we differentiate both sides with respect to a. So on LHS we get di by dA is equal to, on RHS we'll get integral of partial derivative of this integrand, say capital F, with respect to a keeping x constant into dx. Since x is constant, sin x by x is also constant, and differentiation of e raised to minus ax with respect to a is e raised to minus ax into minus x. Now this x and this x will get cancelled. We will be left with e raised to minus ax into sin x as an integrand. This minus sign I am taking outside. Now we will use integration by parts rule to evaluate this integral. We have a standard formula for this integral, which is integral of e raised to ax into sin bx dx is equal to e raised to ax upon a square plus b square into a sin bx minus b cos bx. So we take a is equal to minus a here and b is equal to 1 here, and we write answer of this integral as minus of e raised to minus ax upon a square plus 1 into minus a sin x minus cos x over the limit 0 to infinity. Now let us substitute these limits in x. When we substitute upper limit infinity in x, we get e raised to minus infinity, which is 0. So 0 into anything is 0. So by substituting upper limit infinity in this, we get 0. Now let us substitute lower limit 0 in x. So after substituting 0 in x, we'll have e raised to 0, that is 1, upon a square plus 1 into minus a sin 0 is 0, so this term becomes 0, minus cos 0, and cos 0 is 1, so we get 1 here. So after simplifying, we get di by dA value as minus 1 upon a square plus 1. You can pause the video and check this calculation. Let us carry forward this step. Next, we integrate both the sides with respect to a to get value of I of a. So on LHS, we'll get I of a, and on RHS, we'll get minus integration of 1 upon a square plus 1, that is tan inverse of a plus integration constant c. Next, we will find out value of c by substituting one of the value of these limits as a. So let us substitute a is equal to infinity in this equation number 2. So we get I of infinity is equal to minus tan inverse of infinity plus c. But tan inverse of infinity is pi by 2, so I of infinity becomes minus pi by 2 plus c. Now let's calculate I of infinity. To do so, we'll recall equation number 1. This was our equation number 1. We will put a is equal to infinity in this equation number 1 to get I of infinity's value. So I of infinity will be integration of e raised to minus infinity into sin x upon x dx. But e raised to minus infinity is 0 and 0 into anything is 0. So we get I of infinity as integral of 0 dx. And since integral of 0 is 0, I of infinity becomes 0. Let us substitute value of I of infinity into this equation. So we get c is equal to pi by 2. Now substituting value of c back into this equation number 2, we get I of a is equal to minus tan inverse of a plus pi by 2. Now pi by 2 minus tan inverse of a we know as cot inverse of a. Therefore value of I of a is cot inverse of a, which is the required RHS. Hence proof. I hope you understood every step of this solution. Now let us go ahead for next example. Here we are asked to prove value of the integral 1 minus cos ax upon x square dx is equal to pi a upon 2. Let us consider this integral as I of a. We label this equation as number 1. Now we apply DUIS rule and we differentiate both the sides with respect to a. So on LHS, we have di by dA, and on RHS, under this integral sign, we will partially differentiate this integrand with respect to a. We have to keep x constant as this differentiation is partial. So this x square is constant, derivative of 1 is 0, and derivative of minus cos ax is sin ax into x. So this x and this square will get cancelled. We will have integral of sin ax upon x dx. Now to solve this integral, we will use substitution technique. We put ax is equal to t. So x will be t by a and dx will be dt by a. Now let's check limits for t. When x is 0, t will be 0, and when x is infinity, t will also become infinity. So these will be the limits for t. Now let's transform this integral di by dA from x to t. So di by dA now will become integral from 0 to infinity of sin t upon t by a into dt by a. So this a and this a will get cancelled. We will left with integral of sin t by t dt over the limit 0 to infinity. At this point, I want you to recall our previous example where we have proved integral of e raised to minus ax into sin x upon x dx over the limit 0 to infinity is equal to cot inverse of a. Now in this example, we will substitute a is equal to 0. So after substituting a is equal to 0, we get integral of e raised to 0, that is 1, into sin x upon x dx over the limit 0 to infinity as cot inverse of 0. And cot inverse of 0 is pi by 2. So value of this integral is pi by 2. We substitute this value for this integral into this equation. So we get di by dA as pi by 2. Next, we have to integrate this equation both sides with respect to a. So by integrating on LHS, we get I of a, and on RHS, we'll get integration of pi by 2 dA, which is nothing but pi a by 2 plus c. Now to find value of c, we will substitute one of these limits as value of a. So let us substitute a is equal to 0 into this equation number 2. We get I of 0 is equal to pi into 0, that is 0 plus c. So c is equal to I of 0. Now let's calculate I of 0 from equation number 1. This was our equation number 1. In this equation, we are going to substitute a is equal to 0 to get I of 0's value. So I of 0 is integration of 1 minus cos 0, but cos 0 is 1, so we get 1 minus 1 upon x square, that is 0 upon x square, that is 0, and integral of 0 is 0, so I of 0 is 0. Finally, we substitute value of I of 0 over here. We see c is equal to 0. Now we substitute value of c back in equation number 2. We get I of a is equal to pi by 2a. Hence proved. Now let us go ahead for next example. Here we are asked to prove integral of log of 1 plus a cos x upon cos x dx over the limit 0 to pi as pi sine inverse of a, where a varies from 0 to 1. Since a is parameter in this integral, we label this integral as I of a, and we call this equation as equation number 1. Using DUIS rule, we differentiate both the sides with respect to a. On LHS, we get di by dA, whereas on RHS, we get integral of partial derivative of this integrand. Since x is constant here, this 1 by cos x is constant. We keep it aside and we differentiate log of 1 plus a cos x with respect to a. So in next step, we get 1 by cos x as it is. Differentiation of log of 1 plus a cos x is 1 upon 1 plus a cos x into derivative of 1 plus a cos x, which is just cos x. Now this cos x and this cos x will get cancelled. Only 1 upon 1 plus a cos x will be left as an integrand. Now to integrate this, we are going to make use of special substitution, which is tan x by 2 is equal to t. Therefore, x by 2 is equal to tan inverse t, and dx by 2 is equal to 1 upon 1 plus t square into dt. Therefore, dx is equal to 2 upon 1 plus t square dt. I hope you remember one of the trigonometric identity which says cos x is equal to 1 minus tan square x by 2 upon 1 plus tan square x by 2. So in that identity, if I put tan x by 2 is equal to t, I'll get cos x is equal to 1 minus t square upon 1 plus t square. Now we find change in limits for t. When x is 0, t will be tan 0, that is 0. And when x is pi, t will be tan pi by 2, that is infinity. Now with this data, we transform this integral di by dA from variable x to t. We get di by dA is equal to integral from 0 to infinity of 1 upon 1 plus a into cos x is 1 minus t square upon 1 plus t square into dx, that is 2 upon 1 plus t square into dt. Now we equate the denominators of these two terms by cross multiplying this 1 with 1 plus t square, and then we cancel out that 1 plus t square in the denominator with this 1 plus t square. So we get this statement. Next we open these brackets and we try to simplify it. So we get 1 plus t square plus a minus at square. Here we see there are two terms without t square, and these two terms are with t square. So we separate these terms without t square and t square to get 1 upon 1 plus a plus 1 minus a t square. Now let us take out this constant 2 as well as 1 minus a from this denominator. So when we took it out, inside the integral we get 1 upon 1 plus a upon 1 minus a plus t square into dt. Let us carry forward this statement. Here I see that this integral looks like integral of 1 upon alpha square plus t square dt, where alpha is root of 1 plus a upon 1 minus a. And value of this integral will be 1 by alpha into tan inverse t by alpha. So as I said, it is 1 by alpha into tan inverse of t by alpha over the limit 0 to infinity. This 2 by 1 minus a as it is. Now this 1 minus a and under root of 1 minus a will get cancelled and we'll have only under root 1 minus a here. And when we substitute this upper limit infinity in t, we get tan inverse of infinity, which is pi by 2. And when we substitute lower limit 0 in t, we get tan inverse of 0, which is 0. Now we write this under root 1 minus a into under root 1 plus a as 1 minus a into 1 plus a whole raised to half. And 1 minus a into 1 plus a is nothing but 1 minus a square. So we get 1 minus a square raised to half. That is under root of 1 minus a square. This 2 and this 2 will get cancelled. So we get value of di by dA as pi upon under root 1 minus a square. Next we integrate both the sides with respect to a to get value of I of a. So by integration we get I of a is equal to integration of pi by under root of 1 minus a square dA. This pi is constant, we can take it out, and integration of 1 upon under root 1 minus a square dA is sine inverse of a. So we get I of a is equal to pi into sine inverse of a plus c. Next we find the value of c by substituting one of these limits as a. So after substituting a is equal to 0 in this equation number 2, we get I of 0 is equal to pi into sine inverse of 0 plus c. But sine inverse of 0 is 0, so we see c is equal to I of 0. Next, to find value of I of 0, we have to go back to equation number 1, and over here we will put a is equal to 0. So we get I of 0 is equal to integral of log of 1 plus 0 into cos x, that is 0, upon cos x dx. So log of 1 plus 0, that is log 1, is 0. 0 upon cos x is 0. So I of 0 is also 0. We substitute this value of I of 0 over here and see that c is 0. So by substituting value of c in this equation number 2, we get I of a is equal to pi into sine inverse of a, which is the required RHS. Hence proved. Now let us go ahead with the last example. Here we are asked to prove integral of e raised to minus x square into cos 2ax dx over the limit 0 to infinity is equal to under root pi by 2 into e raised to minus a square. Since in this integral a is parameter, we label this integral as I of a and we call this statement as number 1. Next, we apply DUIS rule and we differentiate both sides of this equation 1 with respect to a. We see it is equal to di by dA is equal to integral of partial derivative of this integrand with respect to a into dx. Since x is constant, e raised to minus x square will remain constant, and derivative of cos 2ax with respect to a is minus sine 2ax into 2x. Now let's evaluate this integral using integration by parts rule. by taking sine 2ax as u and minus e raised to minus x square 2x as v. So by parts rule, we see value of this integral is u into integration of v dx minus integration of v into derivative of u dx. Let us evaluate these integrals, that is integral of v. To do so, we are going to use substitution x square is equal to t. Therefore, we get 2x dx is equal to dt. Now let us see limits for t. Here, when we substitute x is equal to 0, we see t is also 0. And when we put x is equal to infinity, we see t is also infinity. So limits of t will vary from 0 to infinity, just like limits of x. Now let's transform this integral. So we will have RHS as sine 2ax into integral of minus e raised to minus t, and this 2x dx will become dt minus integral of once again minus e raised to minus t dt into derivative of sine 2ax dx as it is. Integral of e raised to minus t is e raised to minus t upon minus 1. So that minus and this minus will get cancelled. So we will left with sine 2ax into e raised to minus t over the limit 0 to infinity minus integral of, and this integral is once again e raised to minus t into derivative of sine 2ax dx. Let us carry forward this statement. Now we substitute these limits in t. When we substitute this upper limit infinity in t, that is in x square, we see e raised to minus infinity is 0. Similarly, when we substitute this lower limit 0 in x, we see sine 2a into 0, that is sine 0 is 0. So by substituting both limits, we get answer 0. This minus sign as it is into integral of e raised to minus t, that is e raised to minus x square, into derivative of sine 2ax is cos 2ax into 2a dx. Next, we take out this constant 2a. We get minus 2a into integral of e raised to minus x square into cos 2ax dx over the limit 0 to infinity. But this integral is nothing but I of a. Look at this equation number 1. So we replace this integral with I to get di by dA is equal to minus 2ai. Next, we take this I on the other side and dA on RHS. We get di by I is equal to minus 2a dA. Now we integrate both the sides. We see LHS becomes log of I, because integration of 1 by I is log I, and integration of minus 2a is minus a square plus integration constant c. Now we will replace this c with new constant, say log of c1. So we get log of I is equal to minus a square plus log c1. Taking this log c1 on the other side, we get minus a square is equal to log I minus log c1, that is log I by c1. Next, we take exponential of both the sides to get I by c1 is equal to e raised to minus a square. Then taking this c1 on the other side, we get I is equal to c1 e raised to minus a square. Now let's try to find out value of this constant c1. To do so, we will substitute one of these limits into this equation as a. So we put a is equal to 0 into this equation. So this LHS becomes I of 0 and RHS will be c1 e raised to 0, that is just c1, because e raised to 0 is 1. Now to find out value of I of 0, we will refer equation 1 and we will put a is equal to 0 into this equation. So I of 0 will be integral of e raised to minus x square into cos 0, that is 1 dx. Now to evaluate this integral, we have to use a substitution x square is equal to t. Since x square is equal to t, x will be t raised to half. Therefore, dx will be half t raised to minus half dt. And when x is 0, t will be 0, and when x is infinity, t will be infinity. Then after transforming this integral, we will see value of that new integral will be gamma half upon 2. You can pause the video and write the calculation that I just told you. And now, since we know value of gamma half is root pi, value of I of 0 will become root pi by 2. Therefore, from this equation, we can say C1 is also root pi by 2. Now we put this value of C1 back in equation number 2, which I forgot to mention over here. So I will be equal to root pi by 2 into e raised to minus a square. Hence proof. I hope guys you understood all the steps in the solutions that we have discussed today. In my next video, we will see examples with 2 parameters involved. Till then, thank you all of you. Thank you for watching this video. Please subscribe my YouTube channel and press the bell icon to get updates about my new videos.